Okay, and welcome to this brief presentation on methods of differentiation. If you've seen the previous video on differentiation of products, this video, which relates to differentiation of quotients, follows a similar pattern. A quotient in mathematics is a fraction, so unlike the products which we looked at previously, where we had two functions of x multiplied together, a quotient by definition is two functions of x that are divided by each other. So in this case we've got y is equal to 4x cubed, that's a function of x, and we're divided by, I'm using a slash here for division, we're divided by cos of x. So this by definition is now a quotient problem. To differentiate a quotient, we need to use the quotient rule. It's stated here without proof to save time on the presentation. I'm primarily going to look at the application of the quotient rule in solving quotient problems. With the quotient rule, the first differential, which is what we're trying to find, dy by dx, is equal to v multiplied by the differential of u with respect to x. Then we take away u times the differential of v with respect to x, and the whole expression there is divided by v squared. Okay, looking at example 2 here, we're asked to find the differential coefficient of y equals 4 times sine 5x, or divided by 5x to the 4. So we're given our function to differentiate here. It's in the form of a quotient because it's a fraction, it's u divided by v. So in this case we will let u be the numerator, which is 4 sine 5x, and we'll let v be the denominator, which is 5x to the 4. I've given my quotient rule to find my dy by dx term. I know what u and v are because I've defined them myself, but I do need to find du dx and I need to find dv dx. So we're going to do that next. So to find du dx, I'm going to differentiate the 4 sine 5x with respect to x, and if you follow the standard form through, because that's a standard function, that will give you 20 cos 5x. To find my dv dx term, I'm going to differentiate the 5x to the 4, polynomial format. Again, if you follow the standard form through, that will give you 20x cubed. So my dy by dx, my first differential, I'm now going to put all my terms into the quotient formula. So if I go to the formula, it says I've got v, and v in this case is 5x to the 4. I'm multiplying that by the differential of u with respect to x, so du dx, and du dx in this case is the 20 cos 5x. And I'm taking away the next expression, which is u, which is 4 sine 5x in my case, and I'm multiplying the u by dv dx, which in this case is 20x cubed. The whole thing is divided by v squared. V in this case is 5x to the 4, and it's going to be squared. So there's my quotient rule applied, and if you like, my differentiation is effectively done here, but I do need to simplify the expression as it's quite messy in that form. Okay, continuing with the example, I've repeated the first line for convenience here. I'm simplifying now the function. All these steps really are simplifying the expression. So 5 times the 20 gives me the 100, so 100x to the 4, and then it's times by cos 5x, so just tidying that first term up, and I'm taking away the 4 times 20, so 4 times 20 is giving me 80, so that's where the 80 comes from. I'm bringing the x cubed before the sine function, and putting my sine 5x at the end of the expression, just a convention to put the polynomials before the trig functions. On the bottom line, the denominator, don't forget this is a squared term, so 5 squared would give me 25, that's where 25 comes from, and don't forget the x to the 4 raised to the power 2, using the third law of indices, will give me x to the 8, x to the 4 times 2 we've got there, third law of indices. Now I'm factorising. I can see that 20 is common to both terms in the numerator, so 20 comes outside, and the highest common factor for the x is x cubed in this case. This will then leave me inside the bracket 5x cos 5x and take away 4 sine 5x. If you expand the brackets there, you'll get back to the previous line. I've left the denominator the same here. In this line here, again, further simplification. On the top, I've cancelled the x cubed with the x8 on the bottom to give me x to the 5. That's a second law of indices problem. When you're dividing the same bases, x is the base here, you subtract the indice, so effectively that's how I get the 5 on the bottom. And then the bracket 5x times cos 5x take away 4 sine 5x remains the same. What I've further done here is cancelled the 20 and the 25 by 5. 5 goes into 24 times, 5 goes into 25 5 times. So again, just trying to simplify the expression into its simplest form. So eventually I end up with the first differential equation, a dy by dx of the original expression we were asked to consider. Okay, exercise 2 here has 5 parts to it, 5 sub-questions here. I'm actually not going to work through parts A and B at the moment. They are proof questions. I will include the solutions at the end of this presentation for those people that want to see the solutions to those, but I'm not going to go through those in detail. I'm going to predominantly look at questions C, D and E, which are the numerical solutions, and follow the approach we've just used in example 2. Okay, looking at exercise 2, part C here. We're asked to differentiate the function of y equals 2e to the minus 4x divided by 3 sine 5x. So this is a product, the y function of the product here, because we've got the e to the 2e to the 4x divided by 3 sine 5x. So we need to define our u term, which is fairly straightforward here. It will be the numerator, so that's 2e to the minus 4x. We define the v term, which again straightforward, it's the denominator, the 3 sine 5x. We need to find a differential of u with respect to x, and e to the minus 4x is standard form, it's e to the ax. So if you follow the pattern through from your standard differential tables, you'll get minus 8e to the minus 4x. And same with finding the v dx, 3 sine 5x, again sine 5x is standard form, sine ax. If you follow the pattern through, you'll get 15 cos 5x. So now I'm going to apply my quotient rule here to find my first differential, my dy by dx. So following the formula through, v in this case is 3 sine 5x, and I'm multiplying that by du dx, which in this case is the minus 8 e to the minus 4x. I'm subtracting from that, the formula tells me to do my u term, which is 2e to the minus 4x, and I'm multiplying the u term by the differential dv dx, which is 15 cos 5x. I'm dividing then by v squared. V in this case is the 3 sine 5x, and I'm squaring that term. The rest is now simplification. Here I've got minus 24, which has come from the 3 times the minus 8. I've brought the e to the minus 4x to the front and the sine 5x at the back. It's just a convention, constants first, in this case exponentials and then trig functions. I'm taking away, the 30 comes from the 2 times the 15, e to the minus 4x cos 5x. And I'm dividing by, and here I've squared the bracket, so 3 squared gives me 9, and when I square the sine 5x, I get the sine squared 5x term. Okay, trying to factorise, the highest common factor is minus 6e to the minus 4x, so that comes outside the bracket, so inside the bracket I'll get 4 sine 5x, plus in this case because I've taken a negative outside of the bracket, so that minus 6 effectively changed the sign over to an inside, so I need this second term to be actually negative when it's expanded, so I made it positive inside the bracket, and that becomes 5 cos 5x, and I'm dividing by the 9 sine squared 5x. Again, if you expand the brackets there on the top line, you will get back to the previous line. Okay, simplification further here, I just divided the minus 6 and the 9 by 3 to get the minus 2e to the minus 4x, and all the other terms remain the same. So the last few lines there are purely simplification, trying to get the first differential equation, dy by dx, into its simplest form. Okay, I'm going to look at exercise 2 here, part D in this case. We're asked to find the gradient of the curve. Don't forget when it says gradient, that actually means differentiate. The equation we're given to differentiate is y equals 5x times by 2x squared plus 4 in brackets, all raised to the power of minus 1. So be careful with the way the expression is given there. That is actually a quotient because the negative 1 index means reciprocal, so we really have there 5x divided by 2x squared plus 4 in the brackets. So just be careful the way that's written. It's actually a quotient. It looks like a product. We've got to find the gradient at a point, and the point is given as the square root of 3 comma square root of 3 upon 2. Don't forget we read that as x comma y, so the x value there is the square root of 3 and the y value for the coordinate is the square root of 3 upon 2. So rewriting the equation, y equals 5x divided by the 2x squared plus 4, we now have the form of a quotient. So we're going to apply the quotient rule in a moment. We need to define our u term. U in this case will be 5x. V in this case will be 2x squared plus 4. We need to differentiate the u with respect to x. So differentiating 5x with respect to x will give us 5. Differentiating the 2x squared plus 4 will give us 4x. Again, standard forms coming from your standard derivative table. I'm going to apply the quotient rule here to find the first differential of this function. So the dy by the x term, just following the quotient rule through, the v in this case is 2x squared plus 4, and we're multiplying it by the differential of u with respect to x, so that's the 5. We're taking away the 5x, which is the u term, u in this case is 5x, and we're multiplying that by the differential of v with respect to x, which is 4x. We're dividing by the v squared, and v in this case is the 2x squared plus 4, and it's all squared. Don't forget the squared there. Now I'm just trying to start to simplify the expression. So I've multiplied the bracket here by 5, so 2 times 5 gives me the 10, x squared, plus 4 times 5 is 20, and I'm taking away 5 times 4 is 20, x times x is x squared. Dividing it by the bracket, I've decided not to square the bracket, I've left as it is. I think in its form it will be simplest to leave the bracket not squared, not expanded in this particular situation. Looking for like terms now, I've got a 10x squared and a minus 20x squared, so this top line simplifies to 20, take away the 10x squared. In other words, 10x squared take away 20x squared gives me minus 10x squared. Dividing it by my bracketed term. Okay, continuing on, I repeated the top line for convenience here. Now we've got our first differential equation, dy by dx equals to 20 minus 10 x squared, all divided by 2x squared plus 4, all squared. I now got to find the dy by dx, the gradient, when the coordinate given is x is square root of 3 and y is the square root of 3 upon 2. Now in this expression, because it's dy by dx equals to some function of x, I do not need this y term here. This is not going to come into not to be used in this case. I only need the x term because I've only got x terms in my right hand side of the expression, and of course the left hand side equals to dy by dx, not y. So I do not use the square root of 3 upon 2 term in the following calculation. So noting that x is given as a square root of 3, I simply put this value of square root of 3, wherever I see an x in the expression, I will simply put in the square root of 3. Okay, and all the rest is basic arithmetic here. When you square root a square rooted 3, you get 3, and again here square rooted 3, I will get 3, and I think you can probably follow through then using your basic bod maths, follow through the arithmetic on these other lines. Okay, it's just basic arithmetic following through to get to these lines. The final answer for my gradient, my dy by dx, when x is the square root of 3, is given as minus 0.1. Looking at exercise 2 part E here, it says differentiate the function, and we can clearly see it's the product again because we've got y equals t to the 2t in the numerator divided by 2 cos t in the denominator, so it's definitely a quotient problem here. But the thing to be careful of when you look at the y function is this top line, the t e to the 2t, is actually a product. Okay, the bottom line is fine at standard form, it's 2 cos t. So we need to be careful here. It is in the form of a quotient overall, however the numerator is in the form of a product. So we're going to have to bring in the product rule from our previous work here to solve this problem. So if I make u in this case the top line, the t e to the 2t, and I'll make v in this case the bottom line 2 cos t, I need to be very careful with my u. It's actually a product, and I've shown the product rule here using slightly different notation than previously used here. I've got du by dt is as alpha times d beta upon dt plus beta times d alpha upon dt. Don't let that notation bother you. I'm just trying to sort of say I'm applying the product rule locally, if you like. I'm just applying it here in this particular case. So in this case I've made my alpha t and my beta e to the 2t. I'm just really using the product rule here. This is basically conventionally it would be u times the differential of v plus v times the differential of u, basically. Okay. So I end up with my du by dt, which has been derived from the product formula, as 2t e to the 2t plus e to the 2t. So a slight complication there in this part of the process, because my u term was actually a product of the function of t in this case times by a function of t. No such problem with the v. It's a standard differential. Cos t differentiates nicely to minus sine t, so in this case I get minus 2 sine t from my standard tables. I'm now going to apply the quotient rule to this problem. Okay, continuous solution here. I'm now going to differentiate using my quotient rule, so I'm finding dy by dt, which is the notation I'm using here. So my v term, in this case is 2 cos t. I multiply that by my du dt term, which in this case from the product rule is 2t e to the 2t plus e to the 2t. And I'm taking away, as the equation tells me to do, the u, which is t e to the 2t in this case, times by my dv dt, which is minus 2 sine t. The whole thing is divided by the v squared. V in this case is 2 cos t, and I'm squaring it. Okay, from here on in it's basically simplification as I'm working through the expression here. In this case here, I've taken the e to the 2t outside of the bracket, so I get 2 e to the 2t cos of t 2t plus 1. Okay, so just factorising, if you like, there on the e to the 2t. Notice the sign change here. I've gone to a plus because I've got a minus and a minus above, so that makes a plus, and I brought the 2, if you like, in front of the t e to the 2t. So just a bit of a rearrangement there and a change of sign on that term. The minus and the minus making the plus, and then bringing the 2 to the front of the expression, and of course I'm dividing them by the denominator, which in this case I've squared, so 2 squared is 4 and cos t squared is cos squared t. Okay, again I'm factorising here. I'm taking 2e to the 2t outside of the brackets because that's common to both terms on the top line, so that can come outside. So that leaves me then inside the bracket on the top line cos of t times 2t plus 1 in the brackets added to t times the sine of t. That's still divided by the 4 cos t. So what I've done in the next line, I've left the term outside 2e to the 2t, but I've expanded the bracket now, so cos t times 2t is 2t cos t, plus 1 times cos t is cos t, so expanding the brackets there, this term is staying the same, and dividing by denominator. On the final line here, what I've done is I've cancelled the 2 outside with the 4 on the denominator, so that's why the 2 has appeared at the front of the equation and 2 appears in the denominator here, and the rest of the expression is the same. So that's the simplest form I can make for the dy by dt term in this case. Okay, I'm going to leave you with some further problems on differentiating quotients here. 7 questions here to have a look at. Question 1, the u and the v are nicely in standard form, so that should be fine. Question 2, the same u and v are standard form. Question 3, the u there, be careful of the square root sign, don't forget to write that as a fractional index, denominator there is standard form. Question 4, numerator is fine. Be careful of denominator, again it's a square root, write that as a t to the half function. Question 5, be careful with the numerator because that's a product, you know, it's a function of x times a function of x, so I need to look at how we handled that in one of the previous examples. Denominator sine x is fine. And with question 6 and 7, they want you to differentiate the product given, and then they want you to use it for the value stated. Same with question 7, you've given a function to differentiate, and then they want you to use the function. I'll leave you with those. The answers are in the square brackets on the sheet. Okay, just going to return to exercise 2 part A, what I skipped before. Basically, in exercise 2 part A, we're looking to find the differential coefficient of y equals tan ax. This is basically a proof here. So I'm not going to go through this in great detail. The full work solution is here though. With this work, this question, you have to take into account the trig identity cos squared x plus sine squared x equals to 1 as the solution unfolds. The other thing to note, when you're differentiating the tan ax function, you must split it into sine ax divided by cos ax. That's a definition of tan. If you remember, tan x is equal to sine x over cos x. So in this case, your u will be sine ax and your v will be cos ax. And then you can quite easily find the du by dx because these are all standard forms, dv by dx, standard form again. You're going to apply the quotient rule as you have in all the previous questions here, putting in the appropriate values of u, v, du dx and dv dx, okay, which is what's shown in this line here. Overleaf, second part of the solution here. I'm just basically following through it. Again, it's algebraic manipulation all the way through. I'm going to let you wander through that. What you've got to note is when you get to this stage here though, to progress the solution further, this is where you bring in the trig identity. Okay, you're replacing the cos squared ax plus the sine squared ax. You can replace that with 1, okay, and that's from this trig identity. So that's where the 1 comes from, and that's how the solution simplifies. You eventually get down to the a over cos squared ax, and if you note from previous work on trig identities that the secant of the angle is 1 upon cos squared of the angle, in other words sec theta equals 1 upon cos squared theta, you can simplify the final differential dy by dx as, in this case, a times sec squared ax. So that's just going from this line down to this line. We can use the trig definition there. Okay. And the exercise 2b, again, I didn't go through that one because that's another proof. It says determine a derivative, first differential, of y equals sec ax. Again, you need to be aware that sec ax is actually defined as 1 upon cos ax, okay, and as soon as you write it as 1 upon cos ax, you've got a quotient. In this case, u would equal to 1 and v is equal to cos ax, and you can follow through the differentials appropriately there. Okay, so again, I'll leave you to follow that. You just apply the quotient rule, put in your values of u, v, etc., and then follow the process through. What I did do here is the sine ax upon cos ax, of course, is tan ax, and 1 upon cos ax is sec ax. So that's where that final expression comes from. Okay, but I'll let you look at that at your leisure. Okay, thank you for viewing this video. Goodbye.